We're going to break down how an electric car really powers itself, not with one simple battery, but through a high voltage pack running anywhere between 200 and 800 volts, a converter that feeds your 12-volt systems, and a communication network that tells every part when to move. You'll see how these layers create a hidden electrical grid under the hood, managing everything from the motor's pull to the dash light's glow. Stick with me. Once you see how those systems talk to each other, the next step will make a lot more sense. Why EVs run on 3 separate nerve systems instead of 1? Every electric car runs on 3 separate nerve systems instead of 1, and that's not by accident. These layers keep raw power under control and turn complex energy flow into precise movement. Most people assume an EV's strength comes from that single big battery, but what really keeps it alive are those 3 parallel systems constantly in sync. High voltage for propulsion, low voltage for controls, and a data network running the show. Press the pedal and all 3 wake up in order, ready to move energy and instructions down the line. Now you might wonder why engineers didn't just run everything straight off the main battery. Why build a 12-volt circuit, a 400-volt circuit, and then wire in another web just to pass messages around? Here's why. Each system has its own purpose and safety limits. The high voltage pack, usually anywhere between 200 and 800 volts depending on the vehicle or conversion setup, drives the heavy loads. The traction motor, onboard charger, and high demand power units. That range delivers serious current capable of twisting metal but would instantly destroy your control electronics if connected directly. The low voltage side is your control and accessory circuit. It runs logic boards, sensors, lighting, and everyday modules, the stuff that can't tolerate a high voltage surge. Keeping this system separate means you can safely manage functions like door locks or infotainment without risking damage or shock. Any attempt to mix those voltage levels would cook components quicker than a reverse polarity battery hookup. Think of the 2 systems like shop wiring. The high voltage feed is the heavy line that drives welders and lifts. The low voltage loop is what runs your lights and test computers. You keep them apart so one spark from the big feed doesn't wipe out your diagnostic gear. Inside an EV, the principle's the same, with a DC to DC converter sitting in the middle as the bridge. That converter works just like an alternator in a gasoline car. It draws energy from the high voltage battery and converts it down to maintain the 12-volt supply and charge its auxiliary battery. As long as the high pack holds a charge, your low voltage circuit stays alive too. Even when the car's sitting idle, that converter quietly keeps sensors, alarms, and computer modules powered up for remote access or system checks. Floating above both these electrical layers is the 3rd system, the CAN network. This is the car's communication backbone, a 2-wire data line connecting everything that thinks or moves. Every module, the inverter, the battery management system, the drive unit listens in and sends coded messages constantly. At the center of that network sits the vehicle control unit, or VCU, basically, the adult in the room. It decides when the high voltage contactors are safe to close, commands torque requests, and monitors temperatures, voltages, and isolation levels. Before any high current flow begins, the VCU runs through a list of system checks. If even one sensor reports a fault or a bad grounding signal, the VCU refuses to connect the high voltage circuit. That's why a silent communication issue can make the entire car look dead even when all readings seem normal. Here's the kicker. One small fault can freeze all 3 systems. A blown 12-volt fuse can keep the VCU from waking, which means the CAN network never completes its handshakes and the contactors never close. Your motor won't spin, your pack looks charged, yet the car's locked down because the brains never gave permission for power flow. This separation isn't about complexity, it's about control and safety. High current stays sealed inside its own zone. The 12-volt network handles commands and monitoring. The CAN bus ties everything together, making sure current only moves when every condition checks out. Next up, we'll trace exactly how those systems pass energy and data once the car wakes, showing where every amp and message travels, before you even start moving. How energy and data flow through the EV's hidden grid. When the system wakes, everything comes online in sequence. This is where you see how energy and data flow through the EV's hidden grid. The low voltage battery is the first to move. It powers up the vehicle control unit, or VCU. Once that brain is awake, it runs a complete startup handshake across the car's CAN network, checking every module and sensor for proper status. Only when the VCU confirms that all systems agree does it command the high voltage contactors to close, connecting the main pack to the rest of the drive circuit. That's the quiet handoff from logic to muscle, and it's what makes electric power safe enough to handle. After those contactors pull in, high voltage energy flows through the main drive chain. The pack sends direct current into the inverter, which feeds the traction motor. Working alongside that, the DC to DC converter draws a steady sip of power to keep the 12-volt system topped off, much like an alternator would in a gasoline vehicle. You press the accelerator, and the control software takes over, turning energy stored in the pack into smooth torque at the wheels. The inverter is the core of this whole flow. Its first job is turning that DC from the battery into three-phase AC for the motor, shaping frequency and voltage based on the torque request the VCU sends over CAN. But it's a two-way device. When you lift your foot or hit the brakes, the inverter reverses the process. The motor now acts as a generator, creating AC from the spinning wheels. The inverter converts that AC back into DC, sending it upstream to recharge the battery. Every transition happens under software control in milliseconds, balancing driver input with battery protection to make sure power moves only where it's meant to go. That control loop depends completely on data. The VCU stays in constant conversation with the inverter, the battery management system, and the traction motor controller. It measures temperatures, insulation, and current flow, comparing those readings to preset limits before allowing full power output. If you ever wondered why some EVs won't respond after a small wiring tweak, it's because one of those checks didn't line up. Here's where DIY builders hit a wall. A mismatched CAN setup can bring the whole process to a stop. For example, install a new inverter that sends slightly different data or timing, and the VCU won't recognize it. That mismatch looks like a dead pack or failed contactor, but it's really the VCU refusing to energize the system. When any expected signal is missing or out of range, the VCU locks communication down as a safety measure. No contactors, no current, nothing moves. Once every module speaks the same protocol and data set, the system passes its checks, closes the contactors, and drives normally. Even when parked, the low voltage circuit still relies on the high voltage pack through that same DC to DC converter. It keeps relays, alarms, and network modules powered so the car can respond to remote commands or perform thermal management in the background. Without it, the 12-volt supply would drain within hours, leaving the next startup dead at step one. Energy and data in an EV don't just coexist, they supervise each other. Every watt that moves does so under the eye of a control signal, and every signal depends on steady voltage in return. Once you understand that balance, what looks like a maze of wires starts to show a rhythm worth learning before you wire your next project. When you build or troubleshoot an EV, understanding its three-layer system isn't optional, it's your foundation. Once you see how high voltage drives power, low voltage handles logic, and the CAN network keeps them in sync, every fault or conversion step gets simpler. Master the handshake between those layers before you touch wire or code. That's how you prevent shorts, false faults, and dead startups. When each system speaks the same protocol, diagnosing becomes as straightforward as tracing a bad ground. Subscribe for practical how-tos and tool-first tutorials you can use right now in your own garage.